we've seen now how to shift and reflect functions, specifically in the context of parabolas, which are also known as quadratics. And today what we're going to look at is how do we stretch or compress, compress means shrink, a function in the vertical direction. And the first graph that we work on here momentarily is going to illustrate this process of stretching and compressing. And we're given a function here, and it's already been moved, as you can see, right and down, because it's a function f of x equals x minus 2 quantity squared minus 9. And then what we want to graph here is we're going to be graphing g of x, which has the formula 2 times our function. And then we're going to graph h of x, which is going to be 1/2 times our function. And first of all, what it says in A is it says label this graph, f of x. So that's the one on mine that's blue. But now what's going to happen, it says on the grid in a different color, create a graph of g of x that's vertically stretched. Well, vertically stretched 2 times that of f of x. Well, what we have to do, if we're vertically stretching something, is we're going to multiply the y coordinates, because vertical is going to go up or down. We're going to, in this case, multiply all the y coordinates in our original graph by 2. So the first point that I'm looking at is this point -1, 0. We're multiplying the y value of that 0 by 2, but we still get 0. The next one I'm looking at is the y-intercept, which is 0, -5. -5 is the y value of that point. -5 times 2 is -10. Third point, 1, -8. -8 is the y value of that point. -8 times 2 is -16. 2, -9, our vertex here. -9 times 2 is -18. The next point, 3, -8. -8 times 2 is -16. 4, -5. We're multiplying the y's by 2, so -5 times 2 is -10. And then 5, 0. Multiplying the y part of that, 0 times 2 is still 0. And what we just did when we multiplied all of those y values by 2, as you draw your quadratic, can see is we elongated that. We stretched out the blue graph into the green graph. And you can see how it's elongated, how it's stretched. If we look at letter C, now what we're going to do is we're going to vertically compress this. And if you are switching colors, you might switch with the neighbor. But we're vertically working with this. So we're still going to multiply the y coordinate, because vertical, y values, by each of each point. This time we're compressing, which means shrink the graph. So we're going to multiply each y value by 1/2. I'm going back to the blue graph, which is the original graph. Starting at the far left here, our point is -1, 0, but 0 times 1/2 is still 0. On the y-intercept here, the y-axis, we had 0, -5. -5 times 1/2 is -2.5. Next point, 1, -8. The y value, -8 times 1/2 is -4. The vertex, which is 2, -9, multiplying the y value, -9 times 1/2 is -4.5. The next one is 3, -8. We're going to multiply the y value of that point, negative 8 times 1/2, which gives us 4. We have the point 4, negative 5 on the original graph. Negative 5 times 1/2 is negative 2.5. And our last point here is 5, 0. Sorry. No, that's right. 5, 0. 0 times 1/2 is still 0. Again, the concept here is vertically compressing. And I think that the graph illustrates the fact of how we compress that. We took that blue graph and we compressed it. Can't see my hand gesture on the video. We stretched it, we compressed it. Now, as we look at part D here, and actually let me go back and just label my graphs here. The green graph is the g of x, and our orange graph is the h of x. But what points did not vary or did not change on this graph? We changed all of them. Zeros didn't change, and the x's. In fact, we can really condense that statement into the x values didn't change. And the x values didn't change because they're horizontal values. The x values didn't change. So let's take a look at our the idea behind here, and then in a moment we'll get in our folders and take out our chart to fill that in as well. But vertical dilations. So you see that word dilation, and I always think dilation, I think of going to the eye doctor. And the eye doctor puts those special eye drops in your eyes, and then your pupils get super big and you can't see anything. Well, in math, dilation means that it can get bigger, but it also means that it can get smaller. So what happens here when we're vertically stretching something, we have some number in front of the function. So what I'm going to write on our chart in a minute is it's going to be outside. When there's some number in front of the function, that's where we're going to have either a vertical stretch or a vertical compression. If c is greater than 1, and it's going to be a stretch. If c is between 0 and 1, it's going to be a compression, again, which means it's shrinking. And I didn't have you fill in any blanks on here, but let's go to our folders and fill in our chart, continue filling in our chart that we've been working on. This is the last on that front page there. And it's written almost the same here. And it says y equals c times f of x. It says when the absolute value of c is greater than 1. Vertical stretch. And notice that the c is going to be outside of the function. And that's when c is greater than 1. You have a vertical. These are the last two. Vertical compression. And again, c is still outside of the function. Some of you might be thinking, but why does it say the absolute value of c is greater than 1? Well, absolute value means that we're dealing with a positive number. What if we have a negative in front of the 2, for instance? What if we have y equals negative 2x squared? What does the negative do to the function? And what it does is it reflects the graph. So we only want to look at the part of it that's going to stretch. The negative reflects, so then we just have to look at the number. So that's why we only want to deal with that positive part of that value to determine the vertical stretch and compress. So if we go back to our notes here and we flip them over, let's look at a couple more of examples. The key, again, with vertical stretching and compressing is we're multiplying the y value in the problem. As we look at this example, number 2, before we even start, what I can recommend is let's mark up some key points on this graph. For instance, the vertex at -3, -1. And then we have a couple more points at 0, -2, and 0, -4. Sorry, -2, 0, and -4, 0. Another value I see is here at -1, 3, and -5, 3. And there's more, but that'll get us good enough. We'll look at the graph marked up a little bit. That's the graph of f of x. And then what we want to do now is we want to consider the function y equals g of x, which is 3 times f of x minus 2. So first of all, let's identify what's happening to the graph and read the equation left to right. So the first thing that we want to look at is, what does the 3 do to the function? Well, what the 3 does to this function is it vertically stretches the function. And I'm even going to add in by a factor of 3. That's what it says. Times 3 is my abbreviation there. By 3. That means in a moment we're going to have to multiply all our points, our y values of our points, by 3. But we also have in here, we have minus 2, and how does minus 2 change our function, transform our function? We're going to go down 2 spaces. Now it says specify both the transformations in their order. So we're going to do the order in which they're written. And that's why I recommend that you start left and go right on the equations. When we come over here to graph, you may want to use your colored pencils because we've got 2 things happening. The first thing that I'm going to look at is strictly the vertical stretch. And once again, the vertical stretch says that we're going to multiply every y value by 3. So going to the left here, we have -5, 3. Our y value is 3. 3 times 3 is 9. So we're going to put our point here. We have -4, 0. 0 times 3 is 0. From our vertex, -3, -1. -1 times 3 is 3. And where am I getting that 3? It's 3 times f of x. -2, 0. 0 times 3 is still 0. And our last point over here is -1, 3. 3 times 3 is 9. Now that's the stretch part of it. I don't typically connect the points on that. But now that we've done that part here, the next part says that we want to move our graph down 2. So this is where I'm going to switch colors here. And I'm going to move every point down 2. We've stretched it down 2. We stretched it down 2. Stretched it, now move it down 2. Move down 2. It's going to be all those red points are moving down 2 to the pinkish purple color. And this is going to give us the picture of our quadratic here. Again, I didn't connect the red points. There's nothing wrong with that. Our pinkish purple color is the g of x when we graph and labeled y equals g of x. So hopefully now we kind of get the idea of vertically stretching and compressing. This one is a stretch, as we saw. But we're not just looking at the stretches, we're starting to integrate in our other concepts. We're starting to integrate in moving right or left or up or down with that. As we take a look at example number 3, it says if the quadratic function g of x has a y-intercept of 0, 12, which of the following is true about the function h of x equals 3 times g of x minus 5? Explain your reasons why / show work to justify your answer. The first thing that we need to know is, how do we write the ordered pair of a y-intercept? And we write the ordered pair of a y-intercept as 0, 12. So that 12 value is the y value. And what we have in our formula is we have 3 times g of x minus 5. Well, that 3 is a stretch on this problem. So in other words, what we're going to do is we're going to take 3, what we did on the last problem even, is we multiplied by 3, and we're multiplying all our y values, but we're looking at one specific y value. After we had that graphed, then we moved it down. Well, guess what? This one's minus 5. This one's going to be moving it down as well. So here's showing work to justify our answer. 3 times 12 is 36. Minus 5 is 31. So what we see here is, which of these has a y-intercept? It's the y-intercept of 31. As we finish, on the graph of f of x below, sketch a graph of 1/2 f of x, and then sketch the graph of 1/2 f of x minus 2. So now what we're looking at is we're looking at a vertical compression, because the 1/2 is a value between 0 and 1. So this is going to be a vertical compress by 1/2. But whether we stretch or whether we compress, it's all about multiplying the y value by how much we're stretching or compressing. So as I start to the left on our graph here, 1, 2, 3, 4, -5, -3. -3 times 1/2 is -1 and 1/2. Next point, -4, 2. 2 times 1/2 is 1. Next point, 3, 5. 5 times 1/2 is 2.5. At our vertex, which is -2, 6, half of 6 is 3. It's our y value that we're multiplying by. We're multiplying by 1/2 because 1/2 is in front of the function. The next one is -1, 5. Well, 5 times 1/2 is 2.5. Our y-intercept, 0, 2. 2 times 1/2 is 1. And finally, the last point on our graph over here is 1, -3, and -3 times 1/2 is -1.5. So here is our vertical compression. Now when we get over here to the right-hand graph, what we're going to do is we're going to do -2. The -2 is inside the function, and how does that change our function? What does minus 2 inside the function do to the function? Thank you. We're going to go right. Now we're going to take our pinkish colored graph, and we're going to move every point 2 spaces to the right. So this point over here at 1, 2, 3, 4, 5, negative 1.5 is going to be at negative 3, 1.5. Our next point, which is 1, 2, 3, negative 4, 1. Negative 4, 1 is going to move right 2 spaces. Our point 1, 2, 3, negative 3, 2.5 is going to move right 2 spaces. Our vertex at 1, 2, up 3 is going to move right 2 spaces. And we continue to move our points right 2 spaces. And here. And here. All of those pink points there, we're moving them right 2 spaces. And then we'll have our complete function of 1/2 times the function minus 2. 1/2 f of the quantity of x minus 2 is said better.